And so yeah, today we're going to have a Q&A session with the professor. I'm going to start with a few questions of our own, and then you will also have the opportunity to throw around our little box of microphone and to ask questions that you may have. But I'm going to begin with why are you in Riga today?
Okay. First of all, thank you very much. It's a pleasure to be here to answer maybe your questions. And why I'm here this time, I'm here because of a PhD examination, which was yesterday. And it was, of course, successful. It was a very good presentation and a very good work, thesis, and so I enjoyed it, and so therefore I was here this time.
And you're here as
I was a reviewer.
A reviewer, yes.
Because 3 reviews are needed, yeah, and I was one of the reviewers.
Yeah. So someone successfully got their PhD today.
Yes, exactly.
Very well. Have you been in Latvia before?
Yeah, sure. I have to go back to the beginning. We have worked together with Riga University, Latvian University, since nearly 40 years. Yeah. So in the year 1985, maybe it's before, Professor Jakovic came to Hanover, to our institute. I was a young PhD student. I was already nearly at the end of my PhD work, and we met at that time. We stayed together in one room for 10 months. So that was the beginning of a very long cooperation since this 85, and of course this was different times. At that time, Latvia belongs to the Soviet Union, and then in the beginning of the 90s, or already 89, an official cooperation contract was signed between our universities, and from that time we had a very strong cooperation. But I have to add maybe that at that time maybe you will ask me about my scientific education.
Yeah,
that's what I talk about now, because it has to do with it. Yeah. Yes. Okay, so I said already that in 85 I was nearly at the end of my PhD work. I have, after school, I finished my school in 72. And after school, I went to Hanover University to start studies in electrical engineering. Yeah. The basics, the reason was, of course, when I was a young boy, I was very interested in techniques and technology, and especially in electronics, because maybe you know, in the 60s, there was the first transistors came up. So not so long ago, before it was tubes, and the first transistors, and this was very, for me, impressive. So I started to work out at home some circuits, electronics for music, for example, but also for the radio distribution, So that was the beginning, and therefore was my aim to study electrical engineering. Of course, when I started my studies, I had to learn that a lot of theoretical work I have to do, and of course, electrical engineering is not only engineering. A lot of physical background you have to know, because it's not something like mechanical engineering. Mechanical engineering you can put your hand on, but electronics, that is something
you can't really see it. Inside the
so you need mathematics, you need physics, and then you can study electrical engineering. Okay, then I during my studies I detected that electronics is not everything. So at the end I switched a little bit to energy engineering, and especially to electromagnetic engineering. So this is my
today's theme for
my career started. Yes, a little bit. Yeah. So I made my at that time it was a diploma thesis. Yeah, because at that time diploma was the final degree, not master, and I made it in induction heating already. So it's one part of electromagnetic applications. So and then due to this diploma thesis, yeah, today master thesis, I got into contact with the Institute of Electrotechnology, yeah, because I made it in this institute, and because at that time there was a new professor, and he watched my presentation of my diploma thesis, and he was impressed, and of course he needed some new stuff, yeah, and he asked me if I were like to start in his institute, yeah, and at that time the situation in industry was not so good, yeah, to get a job, and
so you chose research in
so I
industry.
decided to go to research,
Yeah.
yeah. So and then okay, I started my PhD. I began to start my PhD. The topic were induction heating. Yeah, one of the topics we talked of electromagnetic applications, and so I made my PhD thesis in simulation. Yeah, today everybody talks about numerical simulation. At that time, it was quite new. Yeah, so I wrote the first codes for induction heating simulation, and I was successful, and then I finished my PhD. This was the time when we met, yeah, and so in '87 I finished my PhD. My professor told me, please stay at the institute a little bit more, because we are getting a large project, yeah, about induction melting. And this was a project between industry and institute. And so I started this work, but then in '89 I changed to industry.
And what industry specifically?
It was industry, it was for induction, of course, for induction, yeah. It was, maybe you know, a famous company, ABB. Do you know? ABB is like Siemens. Siemens, you know, I guess you know. ABB is the most competitor in today energy supplies and others, yeah. And so, but this company has a small department for induction applications, yeah. So when I started there, first I was a calculation engineer, yeah, because I was coming from simulations and so on. And then I got the responsibility to be responsible for development, first of all in our small company, but then some years later for the worldwide development.
And then what exactly did you develop? Like, what is the use of
okay,
for
let's talk a little bit about the subject, yes. Yes. So this is one big application of electromagnetic processing, as we call it originally, is induction melting, induction heating, hardening belongs to, and yes, maybe these two main things. So induction melting, that means, you know today induction cooking, I guess, no? Because it's very typical. So that means induction induces energy into materials which are conductive, like metals. Yeah? So if you put a pot on your induction coils at home, then if you have an induction cooker, then it will be the energy goes to the metal, it will be heated, and then it goes to water or something else. And the same is in the industry. So you want to melt, for example, steel or iron or copper or aluminium, yeah. And then if it is melted, you can pour it, yeah, and some special products.
So you just like pull a lot of electricity energy through it and generate a lot of heat. Yeah.
Yes, exactly. So the main thing is to generate heat. Yeah, but okay, the students here from the university knows beside heat you generate also forces. Yeah, and this are mixing the melt. And this is a big advantage of to use induction for melting, because you mix the melt, you homogenize it, and so it's a good quality finally. No? Yeah. So this was one direction.
Yeah.
And I was responsible then for the development of new installations, big installations, up to the biggest one at my time was 16 megawatt. Yeah, one installation, one furnace. Today it is in the range of 40 megawatt. Yeah.
And then the big installations like large furnaces basically.
Yeah, furnaces. Yeah.
And how much metal can they melt at once?
So the size is the typical size. It depends on the material, on the metal. For the biggest ones are for steel typically. They are 60 tons.
Wow.
The density of steel is 8, so it means 8 cubic meters roughly. Yeah, 8 cubic meters. So the diameter is roughly 3 meters of such of the melt only. Yeah, the furnace maybe 5 meters. Yeah. So these are very big installations, and of course, each furnace has to be designed for itself, so that it's not a serious production, of course. So such a furnace costs roughly 1 million, 2 million, yeah? Such a big one. So each furnace you have to design by itself, and this means you need, of course, calculation methods. Yeah, you cannot make any mistake. Yeah, then 2 millions are lost. Yeah?
Why can't the furnaces be like mass produced? Why do they have to be like specifically? Why can't the furnaces be mass produced? Why can you? Why do you have to specify each one?
Ah, okay. Now, because each furnace has a little bit different aim. Yeah. So maybe the power is different. Okay, it is in my development. I try to modelize it. Yeah. At least not. Finally, not to calculate each furnace by itself, but in any case, at least one type you have to calculate. Yeah, that's true. You know. But there are other furnaces, special applications. Yeah, these furnaces really have to be designed one by one.
Okay. So you came from the research fields?
I came from the research field. Yeah, I brought, of course, a big knowledge in simulation, calculation. Therefore,
but you have now moved back to research, as I understand.
Yeah, okay. And okay, but between was another step, because if you are in industry, you can say, okay, development is necessary, yeah. But the real management, then you have to earn money, yeah, in industry. That is typical. Yeah? So in roughly I have been 11 years in industry, and roughly the last half time I was responsible as a manager for a department of this company. Yeah? We call it at that time profit center. Profit means money. Yeah? So I was responsible at least for, of course, for development too, yeah, but also for the profit. Yeah? And this gave me a lot of new, yes, let's say, efforts to calculate something in money, yeah, in the range of millions. Yeah? Which is not so easy, and to be sure at the end that there are not big losses, there is a small profit at least. So, and but then I decided at the end, because this work becomes a little bit boring, day by day, yeah, to make something new. And then I had the opportunity to apply for a professorship in Hanover, in my old institute. Yeah. we have to say that this area of electromagnetic processing is not like the area of electrical machines, drives. Yeah, this is a small area. So the people who can apply in this field are very, very small. Yeah. So I had good chances, yeah, because I was coming from the institute, and then I got really this professorship, and I started in the year 2000. Yeah. So I have been 11 years in industry, and then I changed to research, and then of course the field was much wider. Yeah. As a professor, you can decide by yourself what to do. Yeah? You only have to teach, that is your duty, but research is up to you. Yeah? And I decided to go in some new fields, yeah? Not only melting. I stayed with melting, but also in induction hardening, in induction forging, in skull melting, that is the melting of oxides, yeah? which is not so easy like metals. Yeah? And so I had 22 years in research with very new fields. Yeah.
And all these fields are something that your institute now researches? So,
yeah. Okay, I have to mention my old institute, yeah, because meanwhile I'm retired. Yeah.
Oh, okay, yeah.
since nearly 2 years already. Mm-hmm. Yeah. And I have a successor. It's a colleague which we had already a long time, and but of course in this time I was involved in many new areas of electromagnetic processing, as we officially call it. Yeah.
Did you have the chance to work on some publications together with the Latvian scientists?
Yes, of course. Okay, no, I have to come back to our cooperation. Yeah. So, as I said, we started in '85, but then of course it was not so extensive in the first time because this was the old Soviet times. And from the '89, after signing the contract, it was intensified. Okay, I was in industry, but still we had contacts. Yeah, Professor Jakovic also worked for my industry company, but I have to say always mostly together with the institute. And so, but when I came back to institute, we intensified again our cooperation. And yes, we had a lot of publications together. I haven't counted, but maybe 50, I guess so. Yeah.
And so you work with the Institute of here? Was it? What was the name? I'm forgetting the English name.
My name is Jakovic, but we had laboratory for numerical modeling of technological processes. Yeah. Nowadays it's called Institute for Numerical Modeling. We have in this building 5th floor.
Yeah. And of course this fits completely to our institute.
Yeah.
So we were engineers, yeah, and the colleagues there were from physics, yeah, and especially from modeling, yeah. So they teach us in how to model and how to create new models. Yeah? So that was a big advantage for us, and we had not only publications, of course. First of all, we had an exchange of PhD students all the time. People from Latvian University worked in our institute. Yeah, also worked during their PhD. Yeah, they made their exams here in Latvia, yeah, because it was not so easy to do it in Hanover, but the practical work has been in Hanover. Yeah. 3 years, yeah, sometimes 4 years.
So it's very usual that people go to like other countries and their institutes to work on their PhDs or to do research.
Yeah, we have this. Of course, I have to say yes. Yeah. That is typical for research today. Yeah? You have to be international. You have to look what other universities are doing, and of course, universities are also have to make not profit, but at least to get money. Yeah, not small money is coming from the government. Yeah, but you need third-party money, as we call it. Yeah, so this money can come from can be national money, in my case from Germany or here in Latvia, but also from European community. Yeah, and if you want to have money from European community, we have to work together with other countries. Yeah, so sometimes maybe 10 or 12 or 20 countries. Yeah? So it's clear that in research you have to work together with other universities. It's, of course, it's nice sometimes because you have to visit then these other universities, you have to be abroad, and I really enjoyed this always when we had this big.
And how many countries have you visited this way or worked together with?
Okay, we had our, let's say we had our very intensive cooperation. I have to say very intensive with Russia. Yeah? This has to do with the field of our work, because electromagnetic processing, there are, you can go to the US, but you will find there are only a few institutes which are working on electromagnetic processing. But if you go to Russia, for example, you can find it at any large university. And then you have the centers in Europe. Yeah? Riga, of course, is one main center for, at least for liquid applications. Yeah? Then there is a center in Italy, in Padua. Just my colleague came yesterday from this university in Padua. So it means in each, more or less in each European country, you have one center. At least in the larger countries, you have one center. In France, it is in Grenoble. Yeah? And of course, then you have to go there. Yeah. To present something or to ask to work together. Yeah.
And when you work together with them, how does this process work when several scientists from different institutes, different countries work together? How do you organize this research work?
Nice. Okay. Typically, you have. Okay, first of all, there are different kinds of. One is that you really make an application, for example, to European community. And then, of course, you have to have a project leader. Yeah? First of all, who has the idea, mostly is a project leader. Then you have to go around, look around, who could be interested, from which country, and then you will ask. And then if you really get this project, then you make a kick-off meeting, yeah, typically, and then we meet all colleagues, new colleagues. And as a project leader, I once have been a project leader for a big project with European universities and Russian universities, and you have to organize it. Of course, you have your staff in the university, which you can give something, but mainly you by yourself, you have to organize it. No?
And organize not just your own scientists, but then also the scientists from other countries and this collaboration between countries, is it necessary? Why is it needed? Why do researchers do this? And why not just stay in your own institute, for example?
Okay, of course, in each other university you have new ideas. Yeah, you have. For example, in our institute we had the knowledge in engineering. We have a big laboratory. Yeah? In electromagnetic processing, you need the applications need different frequencies. For example, this is the most important thing: frequency, because with the frequency you can control and optimize the process. And so our institute had a lot of frequency generators, yeah, so our colleagues from Riga like to come to Hanover to use these generators, yeah, because they don't have. They have maybe a small one, yeah. So that means our advantage was we have the lab installations. We are engineers. And our colleagues in Riga came from physics. They are specialists in modeling, yeah. And what else to work together, yeah. And so maybe other colleagues from other universities, they have experience in other fields, yeah. For example, we started one new field. I told already, skull melting. That means inductive melting of oxide materials like zirconium oxide, yeah. It is not so easy because it's not a metal, yeah. It's very weak conductive, and it becomes conductive only if it is liquid, yeah. So it's solid, it's an insulator. And the biggest knowledge is in St. Petersburg, in Russia, yeah. So we went to the colleagues in Russia, please give us your expertise, yeah. But the installation we installed in Hanover, yeah? Because we wanted, of course, to develop a close to industrial size installation, and so that means we worked together for 15 years. Yeah?
So it's differing expertises, different materials.
Yeah. So it's difficult for these operations.
So you're no longer a scientist now, but what does a day-to-day work and life of a scientist look like?
Of a scientist or of a professor?
Well, each, I guess. We can talk about both.
Okay. Let's say of a scientist. When I was a PhD student, of course I had to teach. Yeah, that is to train yourself in teaching the students. Yeah, and then the main work was, of course, to make your PhD work, and there is a little bit different if you make your PhD in Germany at least, and in engineering, you are not only responsible for your own PhD work. You get this has to do. You get full money. Yeah, you get nearly the same money as when you will start in industry, but you have to be a kind of project manager already. That means in electrical engineering, mechanical engineering, civil engineering, you have your PhD work on one side. This is theoretical research, but you have to try to apply your results or the models you have developed already for industrial applications. This has the advantage that you see already what could be, what is the purpose of your research. And the other advantage is you get already in contact with the industry. For an engineer it is necessary because you have to finally, if you leave the university, you have to come to industry and to work there. So, so that means your own PhD work as a scientist, yeah, but also real projects, yeah, and teaching. Yeah. So, if you are a professor, you have to organize this, your PhD students. Of course, you have to let's say, guide a little bit what they maybe sometimes to give them good ideas. If they have a PhD student has to work first of all by himself, yeah. But of course, you have to guide him as a professor a little bit. And of course, as a professor working at the university, you have to do a lot of administrative work. That is, and meetings, yeah, and you have to work in the councils and so on.
That sounds like really interesting because so does every PhD work need to be connected to industry already?
No. That is in engineering institutes, typically yes.
It's preferable.
Because yeah, that has to do with the money, yeah. Because our institute, for example, we had roughly 20 people working, 15 scientists, and only 5 of them, no, only 3 of them are financed by the university. The other 12 has to be financed by third-party money. That means either directly from industry or projects sponsored by government or Europe, but together with industry. Yeah? So let's say that most of the PhD works are at least related to practical, in our area, practical work. You know? There are some PhD works where we tried to get contact with the industry, but we were not successful, and then it was a real theoretical work, also successful, yeah. But let's say 80% are related to industry.
Yeah,
at least to practice, yeah.
It's more practical, I guess.
Yeah.
Okay, so more on the education or the necessity of an education part. So in Latvia, we have like a noticeable shortage of students or specialists in STEM fields, that is like science, technology, engineering, mathematics. For example, in physics and mathematics, like teachers and scientists are in very high demand. Is this also the case in Germany, that STEM fields are missing people?
I guess not. I know, okay, it's the other faculty. I was in the faculty of electrical engineering, but I know the physics too. I think they had a lot of students. Yeah. Okay, there was then we discussed already internally a little bit. There was a little bit change, yeah, in the time when I was in the beginning in industry. It was or before, so it was the 80s and 90s years, yeah. That in this time industry looks not so well in Europe, yeah. And then people came and said, we should not develop, or we should not, our efforts on development, we should sell something, yeah? Yeah? And then it came up that maybe the commercial side is more interesting and you could earn more money, yeah? But then after some time, it was clear, without development, without research, you can sell nothing. So you need development and research to sell new products, yeah? And so that was in the middle of the 90s, then it came up that engineers were growing in salaries, yeah? And of course I have to say physicians are always needed also for engineering, at least for new technologies, yeah? Because I said in the beginning, electrical engineering at least and physics are very close together, yeah? Physics is only wider, yeah? And but if you are working in modern electrotechnology, you have to also work together with physics. So that is also, let's say, has influence on the institute in physics. Yeah, that they have also became more and more students. Yeah, and so when I started my studies, we started with 350 students in Hanover. Then it came down to 150, and now it is growing again. Since 10 years it is growing again. Yeah? So, and I guess the same is for the physics area.
So it all started when it was the country that made the decision to like sell more instead of working on the development, instead like.
Yeah, it is. Of course, it is now. It is mostly driven by, let's say, the development of industry. Yeah. About which jobs are interested, which are offered, yeah. And you know, at least in Germany, there is a lack of engineers, or at least of scientists, yeah. We need much more scientists, yeah. And so we are happy that Latvians come to us or others, yeah. Because industry is still growing, yeah. But people are becoming older, yeah. Getting retired, yeah. So you need young scientists, yeah, to replace the old ones. No?
I think before we let the students ask their own questions, I wanted to ask one last one, which you already mentioned a little. What is the difference between physics and engineering? Where do we like draw the line? Where
engineering is more the application of physics, yeah, to really create something, yeah, something which you can use, and the physics is the basis, it's fundamentals, yeah, for that, yeah, and both you need, of course, yeah.
Okay, thank you. Now, do we have a question from the auditorium? Yeah, okay, I see one hand, cool. Let's throw the cube back. all of the sounds, yeah.
You mentioned that when you were younger, you were interested in technology and techniques.
I understand nothing.
Yeah, I think you can.
You mentioned that when you were younger, when you were starting like university, that you were interested in technology and in techniques, and you said it as if you don't care for it now. So I guess what I'm wondering is, what are you interested in now? What are the fields of engineering or physics that excite you the most?
That's not right that I don't care now. No, maybe I said that I started maybe you mean that. I started with electronics.
Sure, yeah.
Yeah, that because it was due to the time, yeah, it was some new field, yeah. And then I decided that maybe engineering is wider, yeah. And then I decided to go to another field, yeah? Energy, for example. That's what you mean, yeah? Is it right?
Yes, it's what I mean, but I'm also asking what excites you today. Like, what are the fields of engineering or physics that you think are the most promising or interesting?
Okay, that's me. Yeah, okay. Of course, there are different fields which are promising, of course. Of course, today, everything related to energy, yeah? Renewable energy, of course, is very, very interesting because that was also some change in the years, yes, during my practical work. In the 90s, end of 90s, everybody said, don't care about energy. Yeah? Energy comes from the wall. Yeah? IT is the word. Yeah. And of course, clear, IT is necessary today. We know everybody. But then, roughly 2005, when we had the first blackouts, yeah, they say, okay, energy is also needed. Yeah? And today we know that energy is the most important one. Without energy, there's nothing. Yeah? And of course, today, renewable energy. So there are different fields. Of course, electronics. Today, electronics is something that is produced. Yeah? No big research anymore. Of course, in computer, to be faster, to be more compressive, and so on. But the principles are clear. But it's still interesting, of course. Yeah? But there are so many different fields today where you can go to. It depends, of course, a little bit in the country where you are living, because finally you have to work there, to have a job there. My son studied mechatronics, yeah, and he is today very happy with this, because mechatronics, it is both mechanical and electrical, you can use everywhere, yeah. And he's also working a little bit in electromagnetics today. And we have a lot of students today, of course, going into pure energy directions, because it's clear it is necessary for the future. Yeah. Is this answering your question a little bit? Okay, fine, thanks.
Any other questions? Yeah.
You said that electromechanical, electromagnetic energy processing is researched much more in Russia than in the United States.
Yes.
Why is that?
from historical point of view. The centers working in electromagnetics are, let's say, in Europe and also in East Europe. Yeah? And that is only due to the history. And it has also something to do with the structure of universities. In the States, you have very high, sophisticated universities, yeah? And not so wide. And maybe electromagnetic processing was not so interesting for them because they could not earn so much money. Yeah? So maybe biotechnology or something like that is much more interesting. Yeah? But mostly I think it has to do with history, yeah? A little bit. Partly also, yeah, okay. Yeah, also Russia, also China is very good in electromagnetic processing, and yeah, in Europe only some special countries I mentioned.
And it might be because like it's a very industrial process, so and I suppose like
no, it has not to do with industrial. You know that in Russia the industrial applications are not always not so good. They were good in research, yeah, but had problems to realize it, yeah. And therefore a lot of research results went to other universities in Western, because they had a lot of researchers in Russia, but industry is still today.
Okay.
Okay. Yeah, this is just answering your question a little bit. In the States, the industries like to sell, yeah? That is to make money, yeah? And this is a little bit different.
I think there was a hand right there, yeah.
Have you made any notable discoveries or inventions?
Sorry?
Have you made any notable discoveries or inventions?
Inventions?
Yeah, like discoveries or anything.
Yeah. Yes, I have, yeah, but of course nothing where you can earn millions. But in our field we made some special inventions, and one was very successful. It is realized today. It's very special. You know, in steel industry, the big use from steel industry are blanks, yeah, for cars, yeah. Yeah, there are sheets for thin sheets for cars, yeah. And how to produce it, yeah. So the classical way is to make a very thick steel bar, yeah, 25 centimeters high, 1 meter wide. So, but this is too thick for a sheet, yeah? And then you have to roll it from 250 millimeters thickness down to 0.8 or something like that. And you can imagine that needs a lot of energy. And to reduce this energy, some developments have been done, not to cast these very thick ones, but to cast already thin ones, yeah? But then you have to have a new technology for heating. And we have invented a new technology to heat it by induction, of course, yeah? Very thin slabs, we call it, yeah? And with a very high power, up to 50 megawatt today. And this was a nice invention, and this is today the state of the art for new steel works, yeah, new steel companies. Yeah? So that was a very good at least the most successful one.
Why do you need a different way to heat a thinner sheet?
Of course, if you cannot roll it in a cold situation because it's steel, it's too strong. Yeah? So you have to heat it up to 1,000 degrees, 1100 roughly, and then you can roll it down. And yes, and how to get this heat in? Gas is not possible because it is a long strip, yeah? And so this is done by induction, very high power immediately, and then rolled down to thin sheets.
But then the thicker sheets weren't heated by induction?
They were heated by gas.
Oh, okay.
No? Yeah.
And why can't the thinner sheets be heated by gas?
Because then you need furnaces which are 100 meter or more long.
Oh, okay. So the sheets were like thinner but bigger.
Of course,
Yeah,
it needs the same production. Yeah.
Ah, yeah.
If they have only the tenth thickness, you need 10 times longer,
Yeah.
and then you would need very long gas furnaces, and this is no more effective.
Okay. Anything else? Yeah.
What could be the next point of focus in physics after energy? For example, if we achieve our goals in energy, what field would be most likely to take over or be the most beneficial to research?
Besides energy.
Yes.
Yeah. Okay. In our area, yeah, it is not a lot of things. So I work especially in crystal growth. Yeah, that is one interesting field for physics. Yeah.
What?
Crystal growth.
Oh, yeah, crystal.
Yeah, so silicon, for example, for solar cells, yeah, or for semiconductors. Yeah. So this is one interesting field. But also, yes, in general, the electromagnetic processing, what we call it, steering, treatment, yeah, to improve the quality of materials and of products. Yeah. So that is the main aim. Yeah. So with electromagnetic processing, you can improve, that is the most aim, you can improve the quality or even to realize new materials. Yeah. And then, for example, let's say titanium, aluminium, which you have to use in aircraft or also in cars. Yeah. This would be impossible without electromagnetic processing. And I always said my students in semiconductor industry, without electromagnetic processing, it would be impossible to create crystals, and that means semiconductors. Yeah. Because you cannot use gas, then the silicon is completely oxidized. Yeah.
The silicon crystal growing is actually like also something that is done in the institutes here in
it is one topic here. I know very
we
well.
have like I think a laboratory deep down in the basement.
Is this answering your question a little bit? Yeah. Okay. Good.
Okay. Yeah.
Have you ever worked with superconductors, and what do you think of energy storage through supercapacitors?
I have worked with superconductors. Yes, it was one big project, one of the European projects. Super storage, not directly. Superconductors, yes. Also for improving efficiency for heating. Yeah, that was a new installation. This is for big aluminium bars. Yeah, and if you want to. You have something aluminium here? No. Maybe you know the frames from windows or from others, aluminium frames, yeah, thin frames. And these are produced by taking a big ingot, 300 millimeter diameter, 1 meter long. You heat it up to 500 degrees centigrade, and then you push it or press it through a small hole. And this hole has the shape of this profile finally. Yeah, like a sausage, yeah, and so you push this aluminium block through, yeah. So this is a typical way. And how to heat this aluminium block? Gas, yeah, but then you have efficiency is not very high. Induction is already better, but also not very good because induction heating for aluminium efficiency is roughly 60% only, yeah. So superconducting magnet, yeah, but it's not possible to use for induction. You need AC, you need alternative current, yeah. But in superconductor it's not possible, so you can use only DC direct current. But you can rotate you can rotate this ingot, and then you have also induction, like a motor, like a generator. And so, the efficiency of this was roughly 90% compared to 60%. So it was a big effort. It was not so successful in industry because this rotating, of course, is a little bit dangerous. You have to rotate by 300 rotations per minute, and then sometimes it's flown away. So it is worked only in some special areas, but at least it was a good job. Super capacitors, I don't exactly know what you mean.
I've just heard something about like using superconductors and you can store energy more efficiently.
Okay, yeah.
Connected to batteries that can last longer.
No, this I haven't worked with. Okay.
There was a hand, I think.
During your years as a researcher and as a PhD student, you prefer theoretical work?
So, again?
During your years as a PhD student and as a researcher, did you prefer experimental work to theoretical work?
If I prefer, or
yes.
By myself? By myself? Or generally?
Experimental work in groups and by yourself.
Okay. Now it depends what is your thesis or your aim in your PhD. It can be pure theoretical, it can be pure practical. But okay, I worked in numerical simulation, and in this case you need both. You need to make your models. This is theoretical, but then you have to verify, to prove your models, and then you need an experiment. And then the next step comes if you want to apply your models for industry. They say, oh, it's nice that you have your models, but can you really show that your models are working? Can you show some product or some result and then you need again an experiment. So these are the three steps. There are models, verification with experiments, and then real application of the models. So I enjoyed it to do everything. Because okay, I'm engineer. That means a researcher and engineer. That means I like to apply also, and I like to see that I was successful.
I think we have time for one more question. We have two hands. Maybe we can do both.
You mentioned if the money has been the main goal, but what if development has been the main goal? Would we have flying cars by now?
Sorry, I have to come closer.
If the development has been the main goal of everything, would we have now flying cars or eternal life?
Okay. That depends what we want to develop and what is necessary. Depends a little bit. You know that we no limit. Must be useful finally, and have the public. That's the question. Yeah. There's another.
So, good afternoon, sir.
Yes.
My name is Mark, and I want to ask you one specific question, and I would like to introduce it a little bit. Firstly, I think it's clear from the fact that all of civilization inventions are based on people's ability to be creative and curious. So they're both affecting everything around us. And based on that, I think creativity is more useful because we can invent something in our head and then make it real. For example, in cinematography, we have science fiction that invents certain items. For example, in Aliens, the automatic doors that we're using now in our grocery stores and all over the place to automatically open. So this knowledge was invented by people and then it was brought to life. and there is a masterpiece work, Back to the Future, where there are not flying cars but floating cars. And my question is, how far are we from developing the hoverboard and hover systems? And if we will develop them, how useful and effective will they be?
Yeah, difficult to answer, of course. I'm always looking forward, for new things to develop and or to investigate. In any case, I have to mention that, at least in my experience, our field was quite small, and we had some dreams, of course, how we can improve these processes and what we can do then with the processes to improve materials, products, and so on. And so we never thought to go back somewhere. Yeah. It's not so completely answering your question, but it's difficult. It's difficult, yeah. Okay.
I think I'll allow one more, okay?
What are the opportunities in Germany for studying engineering, especially aerospace engineering, and how it's studied?
How you can study?
Yes, what are the opportunities to
In
study?
aerospace?
Yes, basic engineering.
Yeah. Okay, not in Hanover University, but of course there are special areas for aerospace engineering in Cologne, for example. There's a famous German research institution, DLR. I don't know what this means, DLR, Deutsche, I don't know, but they are very famous in aerospace. In Bremen, of course, there is an aerospace center. I think it's a question where you can study this. Yeah. Okay, I should look a little bit, but if you go to internet, I think in Bremen University at least should be something, and Cologne and Stuttgart. Stuttgart is another center for DLR. Yeah. But you have to go to internet to check. This is not. We sometimes work together with these institutes because they also sometimes need electromagnetic processing, but we were not so deeply involved in this. Okay. Mm-hmm.
All right. Then today, to end things, we usually like to ask our guests what we call like flash questions. It's going to be like fast choice between two things. You can answer just instinctively. No explanation is needed. Tea or coffee?
Coffee.
Okay. Physics or engineering?
Engineering.
Of course. Teaching or research?
Research.
Okay. Theory or experiment?
Theory.
Theory. Okay. Experiment or simulation?
Simulation.
Electric field or magnetic field?
Magnetic field.
Okay. Inductivity or conductivity?
Inductivity.
Okay. And then the one last, which is the traditional question of ours, sine or cosine?
Sine.
Okay, thank you.
Okay. Thank you very much.